an example of analyzing a polynomial function. Our whole goal here is to try to get a general idea of what this is going to look like without our calculator. We can always use the calculator to check and make sure we got the right idea afterwards, but let's pretend we don't have any of those features. So how do we do this? So let's take a look. First of all, notice that it is a polynomial function. Now I want to just point something out, is that if I were to write the exponent in here, I'd have a 1. And notice that I have an exponent of 2, an exponent of 1. That's an indication of a polynomial function. They're not negative, and they're not fractions or decimals. So the fact that they are whole numbers tells me that it is a polynomial function. All right, well, let's think about what would this graph be similar? What is the power function that this would be similar to? And if I look at this and I think if I were to distribute this up, and no, it's just the first power, so it's just x minus 1. So this x has a power of 1. But if I were to distribute this up, this x plus 3 quantity squared, well, that's going to become x squared plus 3x plus 9. Well, that's an x squared. So this particular area right here has a degree of 2, and if I multiply that with this one with a degree of 1, I will see that I end up with an x cubed. So this is important because that means that this is going to be the power function that I'm similar to, that I'm going to have a similar sort of end behavior as with the x cubed. So let's see, the degree here, degree of 3. And what do I know about that y equals x cubed? Well, if I were to do a little sketch of it, I know it looks something like this. Okay? So I know that this is going to have, we're going to have a similar behavior over here. All right, so now we know that. Well, what does this tell us? Let's think about that. That tells us that as x goes to infinity, so as x is going to infinity, as x is getting larger and larger, what is the function doing? The function is going to infinity as well. So as x goes to infinity, f of x is also going to infinity. All right, well, what's the other way? Well, as x goes to negative infinity, as x is getting smaller and smaller and smaller, what is f of x doing? Well, it's going to negative infinity. So as x is going to negative infinity, f of x is also going to negative infinity. This gives us an idea of our odd function going on here. So these are things that we can conclude so far. So let's kind of recap what we have. We know that right here that this particular function is going to be similar to our power function of x cubed, which has a degree of 3, and we know that this is the sketch of it. And what this tells us with that sketch is that as x gets really large, this entire function is going to shoot up towards infinity. We also know that as x gets really, really small, that this entire function is going to shoot down towards negative infinity. All right, well, let's think of what else we know. So let me recopy this. So we have f of x is equal to our x minus 1 and our x plus 3 squared. All right, well, if we have a degree, if our degree is 3, I also know that the max number of turning points is going to be n minus 1. So if our degree is 3, it's 3 minus 1, which is 2. So 2 is going to be the maximum number of turning points. What do I mean by turning points? I mean that from going from increasing to decreasing to increasing, that sort of turn, there can be only a maximum of 2 turning points. So that is some other key information we know. Now, you know what? I think we're ready to kind of examine where my intercepts might lie. So let's think about this. Okay, so let me change my colors here. Where are my x-intercepts? So where is this entire thing equal to 0? All right, well, for x minus 1 and x plus 3, squared. For that to equal 0, I have x minus 1 equals 0, and I have an x plus 3 squared equals 0. Or in other words, I could just say for that x plus 3 squared equals 0, I just have an x plus 3 equals 0. All right, so I know that if I set them each to 0, I have x is equal to 1. So that is one of my intercepts at 1, comma 0. And then I have x is equal to negative 3. Okay, so now I know my intercepts. I have 1 and negative 3. But one thing I want you to notice that this has an x plus 3 quantity squared. So technically, and if I were to write this out, this is an x plus 3 times x plus 3. So the 0 of x equals negative 3, that particular 0 shows up twice. So we're going to say this x equals negative 3. This 0 is going to have a multiplicity of 2. Now this x equals 1, this 0 shows up once. So this has a multiplicity of 1. So I technically have 3 zeros, which corresponds with the fact that I have a degree of 3. So I have, with a degree of 3, I have, so with our degree of 3, let's just summarize what we have on this new slide. So we see again that on here, we got this particular shape going on, similar to the x cubed. I have 3 zeros. I have x equals 1 with a multiplicity of 1, and x equals negative 3 with a multiplicity of 2. Why is that multiplicity important? First of all, if it has an even multiplicity like this one does, then I know the graph is going to bounce back, or in other words, touch it. So it's going to go ahead and hit at that 0 and then bounce right back from the direction it came. Whereas if it has an odd multiplicity, like in this one, a multiplicity of 1, it's going to cross, it's going to go right through. The last thing I want to just take a look at, where is our y-intercept? And I know for our y-intercept, x is equal to 0. So I have a 0 minus 1 times 0 plus 3 squared. So when x is equal to 0, what is my y value? That's a negative 1 times 3 squared, which is 9, which gives me a negative 9. So I know it crosses the y-axis at 0, negative 9. So when x is 0, I get out a negative 9. All right, let's put all of the pieces together. So we're going to go 1, 2, 3, 4, 5, 6, 7, 8, 9. So way down here. Let me switch colors. Let's put it in green. So we know the behavior, what it's got that idea of what it looks like, meaning that when I go to, when x is greater, it's going to shoot up. When x is negative, it's going to shoot down. Or go, I should say, in the negative direction. So I know I have a 0 at negative 3, so let me put my point here. It has a multiplicity of 2, so it's going to hit it. And then I have a 0 at 1, and it has a multiplicity of 1, which is odd, so it's going to go through it. It's going to hit the y-axis right there at that negative 9. So putting all of the pieces together, I'm going to shoot up, multiplicity of 2, so bounce back down. It's going to go through here. I don't know exactly the minimum, but I know it's coming out through, and then it's going to shoot back up here. So one thing just to make note is I don't know where it bottoms out. I cannot assume that it bottoms out at the 9 and then comes up. So when I graph in my calculator, I can see that it's going to bottom out before it, and then as it's going up to hit this other 0, that's when it's going to go right through it, go through that negative 9 and then through the 1. Okay, so this is an idea, a general idea of how we can get a good idea of what the graph is going to look like in this particular polynomial function. I hope you found this video helpful.